These are ordinary satellite ground stations. They cost millions. And this is a ground station you can build for the newly launched LoRa satellite. It costs less than $20. Let's make one in parallel to the launch of the spacecraft. Will it be successful? Grüezi YouTubers, here is the guy with a Swiss accent, with a new episode and fresh ideas around sensors and microcontrollers. Remember, if you subscribe, you will always sit in the first row. Last Thursday, I announced that the 16-year-old Julian Fernandez and a small team built FossaSat-1, and it will be launched today, Friday 6th December 2019, from New Zealand on board of an Electron rocket. This event took place this morning.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
And it is why I can start to build the ground station and produce this video. In parallel, we will have a look at the mission and how it goes. For the moment, we wait till the satellites are released by the rocket. In parallel with the satellite doing its thing, we can continue with a video, where we will cover the FossaSat-1 program and its current status, how we can track satellites in general and FossaSat in particular, how we can build a ground station and connect it to the internet, how we can create a satellite simulator to test our ground station, and how sensors in the future can look like. Interesting times. Let's start. Julian started the project with an idea and a Reddit post. Then he found 2 team members, and finally they placed a homemade Pico satellite in a nice-looking rocket that was launched this morning. An astonishing story. Let's see what he has to say.
This is FossaSat-1, a 5cm sided cube that will be one of the smallest satellites ever launched into space. It uses the pocket cube form factor, which thanks to its reduced size and use of commercial components, can be launched into space for less than the cost of a car. FossaSat-1's mission is to democratize access to space. It carries a LoRa transceiver, which will create the world's first global, free and open source Internet of Things telecommunications network.
The satellite carries a LoRa repeater and a beacon on board, as well as expandable solar panels and an expandable antenna. It receives and transmits on 436.7 MHz. This is not the ISM band, and you have to ask a fellow ham operator if you want to stay legal with your devices. The idea of the project is that your sensors transmit messages to the satellite. The satellite repeats the messages, and so they arrive at the ground station on Earth. The whole system consists of sensors, satellites, ground stations, and a message transfer backbone from the ground station to our application. As we will later see, one satellite can cover most of the Earth's surface, but of course not all the time. In the meantime, Rocket Lab announced the release of the Pico satellites into space, and we got the first TLE data from Julian. It is not completely clear where the satellite currently is. This is why we got 2 TLEs, FossaSat A and B. We will later see what TLEs are. So let's continue with the video. Let's start with the most attractive part, the satellite itself. It is a low Earth orbit or LEO satellite because its altitude is around 300 to 500 kilometers. This means it moves quite fast around the Earth and always changes its position relative to ground. So the natural question is, where the hell is it? And when can I reach it? To answer these questions, you need information about the track of the satellite and a lot of mathematics. Fortunately, satellite tracks can be accurately forecasted, and we can get programs for precisely that purpose. And we also get a standardized piece of information called two-line element, or short TLE, which describes the track of a satellite. These are the elements of a TLE. I do not know how they get this information, nor do I understand, for example, what the first derivative of mean motion, aka the ballistic coefficient, means. So I am happy about all the helpful software and services. After I got the initial TLEs from Julian, I downloaded a program called gPredict. This program can, based on the TLEs, calculate the current and future position of any satellite. You find a link in the description to the download. After the start of gPredict, you already see many satellites. These are amateur radio satellites. Our FossaSat is not depicted. We first have to get the latest TLE data from a service called Celestrak, a free service that tracks a lot of satellites. To do that, we go to Edit and Update TLE data from network. Usually we get a bunch of new satellite data, and after hitting close, our database is up to date. Next we add a new model and name it Fossa. Then we select the satellite or satellites we want to track and hit OK. You should find the FossaSat-1 in the database and select it. Currently there is no official data, and you find a link in the description to a file where you can upload the data. Because we still are at the beginning of the mission, the satellite track is not completely clear. This is why I got the two TLEs. I will track both of them till I get better information. Now I see the satellites on the world map. We also see their footprint and a lot of other exciting information. The most important info is the next passes. Why? Because my station will probably be the closest to the track during the first European crossing this evening. This is why I print the data on a piece of paper for later reference. The pass will start at 21:10 local time and will last for about 10 minutes. Of course, before you get this pass information, you have to add your home as a ground station. Okay, now we roughly know where the satellite is, how big its footprint is, and when it is reachable next time. So we have to hurry up and build our own ground station. Fortunately, this is simple, because in the days before the start, another team built an infrastructure based on the ground station code from Fossa Systems. They choose a TTGO LoRa board for their project because it has an ESP32 on board and therefore uses the internet to connect to an MQTT server. The MQTT server feeds a Node-RED installation where all ground stations are shown. You should also see messages coming from the satellite and the satellite position on the same map. Impressive what they were able to do with Node-RED, I have to admit. You see a lot of active and passive stations are waiting for the satellite. Not enough. They transfer the messages to the Telegram messenger where for the moment you can see all messages. In the future it is planned that you can connect to your MQTT topic and get your individual messages delivered to your application, similar to TTN. To build such a ground station is easy. We download the sketch from GitHub and if we use a TTGO board, everything should work okay. If your display does not work, please check which pins your board uses for the display and adjust them in pins_arduino.h. Here you see two pinout variants for TTGO LoRa version 2 boards. You find the file in this directory. You get to this directory by clicking here in Preferences and continue along the path mentioned before. Please do not care about the extension V1. Currently there is no V2 board definition available. I just read in Telegram that the beacon of the satellite was heard in Australia. The signal was quite weak compared with the signals transmitted by the two other satellites of the same transport. So hopefully everything is okay. Now I really have to hurry up. When you open the Fossa_ground station INO file, have a quick look at the libraries. Then you can imagine how much work went into this piece of software. After uploading, the ESP32 starts up and creates a hotspot with the name Fossa Ground Station. If you connect to it, you should get this screen. If not, go to 192.168.4.1. Now you have to enter the Wi-Fi credentials, your station name, and the latitude and longitude. This information is used to display your station on the map. So maybe you want to use unprecise numbers here. Then you have to enter the MQTT server. You get your credentials if you fill out a form. You find the link in the description. Today I can use generic credentials. I got them by joining a Telegram group. My golden rule for new systems is, if a system is not tested, we have to assume it does not work. Everything else is just luck. But how to test my ground station before the satellite arrives? Fortunately, I also get a satellite simulator code. I use this Arduino 3.3 volt Nano and an RFM95 module for the simulator. Please do not forget to solder an antenna to the antenna pin. The simulator will transmit, of course. And later on, we can reuse the same setup to build a sensor. A few minutes ago, the satellite passed California. Unfortunately, the ground station near Tucson did not hear anything. Let's concentrate on the work. Only a few hours to go before the first pass. When you watch this video, please add test underscore in front of your station name. Then your messages will be separated. Otherwise, your test messages will disturb the productive environment and you will not be a hero. When you press Save, your ESP reboots, connects to the MQTT server and waits for the satellite messages. You can check if your ground station appears on the map and if it receives messages, and then place your TTGO outside your house where it sees the sky. A standard antenna like that should be okay. By the way, do not forget to stop your simulator immediately after the tests. Of course, it transmits on the same frequency as the satellite. Now I am ready and can continue with the production of this video. Because the two other satellites of the same transport flight transmit signals on 437 MHz, I prepare my two Baofengs with their respective frequencies. Like that, and if I'm happy, I can check if the whole bunch of satellites is above me. What is left? The sensor, of course. Here we have a significant problem to solve. We do not want to waste any energy. LoRa is a very efficient protocol and does not need a lot of energy. So we do not wish to transmit or even receive if no satellite is overhead our sensor. To achieve that, the sensors have to be synchronized with the satellite. For the moment, I only have a first prototype sketch of an Arduino and an SX1278. It waits till it gets data from the satellite to be sure it is visible, and then it transmits the message. Of course, it could also happen that two sensors transmit at the same time. These are all things that have to be optimized over time. I do not expect many sensors in the same area for the next future. It is now a few hours later and after the first pass of the satellite close to my home. I was not able to film outside because I had not enough hands and it was already dark. The result is disillusioning. I tried to contact the satellite during the whole path, but did not get a response. I heard one of the other satellites with my handheld, so communication was possible, also to FossaSat-1. Most probably it is on low power mode, which should not be the case. A station in Germany and many stations in Spain were also inside its footprint, but also did not get any signals. The next path overhead Europe will be tomorrow morning. Nothing to do till then. Julian and his team can have a good sleep and tomorrow morning continue with the investigations. Of course, we all hope that the satellite somehow will recover. This is the story of the first day in the life of FossaSat-1, the first public LoRa satellite. If you are interested, you can follow the next steps by joining the Telegram channel. There you should get first-hand information if the satellite recovered. If you do not want to build your own ground station, you can go to the data channel and see the messages coming from other stations. As a coincidence, today I got two 868 MHz antennas, which will be used in a next LoRa space adventure. Lacuna is a commercial project using LoRa technology on 868 MHz, and it will be compatible with LoRaWAN. One of the founders is Thomas, who ported the LoRaWAN library to the Arduino environment and so helped to start this whole movement. I wish Julian and his team luck, also because I'm curious to send my sensor data to space and get it back from there. I hope this video was useful or at least interesting for you. If true, please consider supporting the channel to secure its future existence. You find the links in the description. Thank you. Bye.